How are we doing, professional pilots? This is Professor Stanford. We're doing Chapter 5 in the Turbine Pilot's Flight Manual, page 73, Major Aircraft Systems. Now in this chapter he deals with flight controls, like our ailerons, flaps, elevators, rudder. And he also has a section on pressurization, environmental systems, and fuel systems. So what we're going to do in this learning module is take the flight controls. It's large enough that it can stand by itself, and it's important enough that you need to know how all these things function. And from a pilot's point of view, it's probably the most interesting of all of them. So let's talk about flight controls on page 73. In yellow here we see one of the reasons that most turbine-powered aircraft must resolve the aerodynamics of high cruise speed with slow flight and high lift required for safe takeoff and landings. So that's what the engineers, the challenge that they're faced with. They want fast cruising speeds to get you from A to B, but you've got to be able to land on a 4,000 to 6,000 foot runway with safety. So in order to do that, they have to configure the aircraft on takeoff and landing so that it can slow down. And like it says down in the next paragraph, high-speed flight is best achieved with small, thin, low camber, swept wings of high wing loading, since these characteristics minimize drag. Okay. Safe takeoffs and landings, on the other hand, are best accomplished using thick, high camber, high lift wings with low wing loading and therefore high drag. So as we'll see as we talk about the leading edge flaps, the trailing edge flaps, that's what they're trying to do. They're trying to increase the camber, also trying to keep the boundary layer on the wing during high angle of attack situations with leading edge devices. So these are the challenges and how they've met them. You can remember that Concorde used to take off out of Kennedy on a regular basis, and to my knowledge it didn't have leading edge devices on it because of the high heat problems of supersonic speed. But they had flaps, spoilers, these other things that contributed to it. Plus, and people don't mention this too often, they had tremendously high thrust engines. So if you can accelerate to these high speeds in a short period of time, that's another way of using a short runway, isn't it? However, the landing gets critical because your high speeds on landing will use up a lot of runway. So, but for takeoffs, when you got 4 afterburner engines, you can really increase the speed dramatically for takeoff. Let's go down and talk about the flaps and leading edge devices, bottom of page 73. So he reiterates the same thing. The combination of high speed, high cruise speed, acceptable takeoff and approach and landing performance is achieved through extensive use of flap and leading edge devices. Goes and talks up here at the top. Turbine aircraft almost without exception use slotted flaps, Fowler flaps, or a combination of the two. So let's talk about a slotted flap first of all. What's slotted in the flap? Well, when extended, these slotted flaps form a space or slot between the leading edge of the flap and the inside of the wing. This gap allows fast-moving, high-pressure air to pass through the slot and over the upper portion of the lowered flap, preventing air separation and increasing the lift produced by the wing when the flap is lowered. So that's a slotted flap. Now what we'll see about the Fowler flap is, what does the Fowler flap do? It creates those slots, but it also, as it says, when extended, moves on tracks aft of the trailing edge of the wing structure instead of hinged down. The benefit of the Fowler flap is that they change the wing's camber and also increase its surface area. So that's the big thing about the Fowler flap. It rolls back on hinges or tracks, increases the camber and the wing surface. As we know, when you increase the wing surface, the lift is increased and you can fly at slower speeds. Goes on to talk about, and says, drag, on the other hand, increases only slightly with the Fowler flap. Did you like that little notice there where it has these little little notes that pop up? That's a little thing I'm trying in this section, so we'll see how that works. Okay, let's go down and talk about leading edge devices down lower here. So we've talked about trailing edge devices, the slotted and Fowler flaps. And let's talk about the leading edge devices. By effectively lowering the angle of attack for the leading edge of the wing, LEDs increase lift by keeping airflow attached over the top of the wing at high angles of attack. Most common leading edge devices are slats and leading edge flaps. So there are a number of these that we'll talk about in particular. Okay, page 74. Slats are secondary airfoils mounted on leading edge of the wing, which when extended increase the wing's camber. Now slats on some of the older aircraft like Boeing 727 were typically mounted on the extended tips of the wing. And the slat would come out, it would extend, and it would, as it says here, they were actuated hydraulically as the flaps were extended. The trailing edge flaps were extended and the slats would come out. So when you extended the first few notches of flap on the approach, the slats would come out on the near the tips of the wings on the forward leading edge of the wing. As from we read here, as slats extend, they form a slotted leading edge, allowing high pressure air from below the wing to flow over the upper portion of the wing and delaying air separation at as trailing edge flaps are extended. So this is the slats that we see. Again, they form a slot in which the air can flow through and up over the top of the wing and keep the boundary layer on during the approach, during high angles of attack. Now the leading edge flaps, as we see here, include nose flaps, sometimes called droop flaps, and then there are the Kruger flaps, and we'll talk about these in some detail. So we'll point them out and we'll use a diagram to show you the difference between them. The effect of each type of flap is to increase the camber and attach airflow over the top of the wing. Goes down and talks about Kruger flaps hinge forward from under the leading edge of the wing, thereby acting as air dams to force airflow over the top of the wing. So as we'll see, I remember seeing this older 727, this Russian guy owned one and he'd fly back and forth to Russia. He was obviously in the financial markets and he had it out at FLK or West Hampton there. And when the aircraft was sitting on the ramp, the Kruger flaps would, because they're hydraulically actuated, they would kind of droop down a little bit sitting on the ramp there with no power on. So you could see the Kruger flaps, and they're inboard, usually from near the fuselage on the leading edge all the way about 2/3 of the way out. The Kruger flaps they have a hinge and they would, from the underside of the wing, fold forward and increase the camber and and also to the degree a little bit of the surface area of the wing. So camber and surface area of the wing would be increased. Now he goes on to talk about a number of things. Flap overspeed protection, we're not going to worry about that too much. Auto slat stall protection system. On page 75 we'll talk about that in due course. But let's go down and have a look at the diagram down below here and just walk you through that. Let's go over this diagram on page 74 with the aircraft and just review some of the things we talked about with trailing and leading edge flaps. Let's go over here and talk about the inboard and outboard flaps. So we've got them on the trailing edge here. We've got the aileron, the high-speed aileron out there. I should say the low-speed aileron out there. And then let's go over to the other side over here. We've got the ground spoilers, which we'll talk about in due course. We've got the aileron. This is the full-time, what we call the high-speed aileron. And these are the outboard ailerons that operate at lower speed out here. So can you understand that? On the landing configuration, these are active out here, plus the inboard aileron. It goes up and down. As we'll note with the spoilers, they just go up in one direction. They don't go beneath the wing. So those are straightforward. Now these are ground spoilers and roll spoilers in flight. They operate along with the ailerons to, and we'll talk about these in due course, but this is a good thing. Come back to this diagram. It's figure 5-1. And if you're having any doubt about the spoiler situations, look at them, and that gives you a better idea of what's going on. Now let's talk about the leading edge devices. These are the slats that we're talking about. These fold forward and down, and they form a slot in between themselves and the wing. And at high angles of attack, that's on takeoff and landing. They allow they increase the camber of the wing, the square area of the wing, and of course with the slot, they allow the airflow over the top of the wing to remain on the wing longer, and therefore you can fly at lower speeds. Now inboard you have the leading edge flaps, the droop flaps, the nose flaps, or the Kruger flaps. Now it's hard to kind of show you the Kruger flaps because they are kind of on the underside of the wing, and they have a hinge underneath there, and they fold forward. These are the normal droop flaps that you'd find on the common aircraft. Let's talk about the slat situation as we left page 74. The auto slat, let's go through that right here. The auto slat stall protection system is designed to automatically extend the leading edge slats to full down position, and this is without the pilot's input. Anytime the stall warning computer detects the aircraft is in an extremely high angle of attack. And in short, the auto slat stall protection enhances the aircraft's stall characteristics by automatically lowering the wing's angle of attack. Okay, so that's the auto slat stall protection system. I'm not familiar with any of the aircraft that have that, but obviously it's out there and available. Let's look at the flap and slat asymmetry protection. This would be one of the slats or the Kruger flaps failing to deploy when you're using them on takeoff or landing. Now there's a famous American Airlines DC-10 accident in Detroit. I forget what year it was in, but they had a problem, and the leading edge devices on the DC-10 failed to operate properly, and they retracted just as the aircraft was taking off. It had lost an engine, a hydraulic system was breached, the fluid was lost on that left-hand side of the aircraft on the leading edge devices, and they folded back under with the air pressure, and it caused the aircraft to roll to the left. The left wing stalled, and the aircraft rolled over, and they got some spectacular video of that DC-10 doing a slow roll before it hit the ground. So this was caused by an asymmetry situation, and on here they've given you a asymmetry flap prevention. So to prevent this from occurring, turbine aircraft have it equipped with the flap and slat asymmetry protection monitors. Goes down and talks about if the system detects an asymmetry situation, it will lock the flaps or the slats in their current position. In other words, it will not allow them to decay or fold back under and cause that serious asymmetry situation that occurred in the DC-10. So that is a pretty important thing. Now they can't fix the situation, but they don't let it deteriorate, and so it locks the flap or the slat in its current position. Now before we leave this section, let's look at some of the trailing edge flaps. We've got the plain flap here, slotted flap. Again, it's that slot in between right here that gives it the aerodynamic performance, and it keeps the flap, the boundary layer on top of the flap, from separating, and so it allows it to fly at a slower speed. And here's the Fowler flap again. As we talked about, the Fowler flap increases the area of the wing and has slats in it, or slots I should say, so that it keeps the boundary layer on the flap and allows you to fly at a lot slower speed. So most large turbojet aircraft have the Fowler slotted flaps with, as we can see here, a double slotted or a triple slotted flap. And so that's an important thing to look at. Let's just drop down here and we'll have a look at the nose flap, or the drooping flap, and the Kruger flap. And so it's interesting to know how that just droops down there, but here's, it's hard to verbally explain, but the Kruger flap has a hinge right there, and it folds forward. This is not in the deployed position here, it's just showing it being deployed, so it folds out and forward like that, so it sits out here. So as you can see, it will increase the camber of the wing and the area, allowing the aircraft to fly at a much slower speed. So with the Fowler flaps, as we see on the trailing edge, and we see a good idea of how these leading edge devices and trailing edge devices operate. So let's move on to ailerons on page 76. If you can go here and just review this, although small ailerons are sufficient for high-speed cruise, they're generally inadequate for effective low-speed roll response. Conversely, ailerons large enough to be effective for low-speed performance may cause over-control situations in high-speed areas. So what they've done is they've set, like it says down here in the 7.6, the Boeing 7.6, they have 2 ailerons per wing. As we saw on the previous diagram, they have 2 ailerons inboard on either side, and of course the normal wingtip ailerons on either side for low speed. So it says a common solution to this problem is installation of multiple ailerons on each wing, separately activated as a function of airspeed. The 7.6 for Boeing has 2 ailerons per wing. The inboard operate continuously, but outboard ailerons operate only below 240 knots to assist roll control at slow speeds. So we'll see as we go down here below that in order to enhance the rolling moment of the aircraft, they have roll spoilers also that help. So let's just move down the page here. So the roll spoiler, they're flat panels mounted on the upper wing surface and used to assist the aileron in roll control. In a turn, they work by deploying one at a time up into the slipstream on the down wing. That's important, the down wing. And they disturbing lift and thereby aiding the downwing aileron in affecting the turn. The downwing aileron is least effective in a turn, as you remember from basic aerodynamics. So this is an in-flight operation. The roll spoilers are for in-flight to assist the ailerons with the turn. He talks about roll spoilers are interconnected with the ailerons so that they perform in harmony with them. Next time you get on an airliner, try and get a seat over the wing so you can see these in operation. They're pretty interesting. As with ailerons, roll spoilers deployment on many turbine aircraft is regulated as a function of airspeed. So we talked about that also. They have 2 roll spoilers deployed on each wing, with ailerons usage below 140 knots, but only 1 operate per wing above that airspeed. So again, the roll spoiler, very important control device on the aircraft. Talk about on the ground spoilers. They also want you to know about the lift dump mechanism, and we'll talk about that in just a minute here. So, as I said here, most large aircraft also require the use of ground spoilers on landing, and we've all seen that. As soon as the aircraft, the weight on the wheels gets down and the squat switch is compressed or activated, the ground spoilers flip up on the top of the wing and kill the lift on the aircraft. So it's pretty hard to do a bad landing on one of those aircraft when you have the ground spoilers deploying to keep you from bouncing. So when one of these guys does bounce he's doing a pretty bad landing. Next point down, ground spoilers usually deploy automatically under some combination of power lever and weight on landing gear. As you can see, the squat switch type thing. If you haven't heard of that before, you should become familiar with the squat switch, usually on the landing gear. Okay, here's the lift dump that they talked about. Some aircraft use lift dump mechanisms for this purpose instead of ground spoilers. Now these, I've seen these on the Hawker 800 executive jet. And as you touch down, it doesn't have they don't have spoilers on the top of the wings, but the flaps are quickly and automatically extended from landing position to nearly 90 degrees. As the slotted flap on such systems extend, they effectively dump the lift of the wing and create a huge or large amount of drag. And that's what the Hawker uses. No top spoilers, but just the lift dump that deploys to increase that large amount of drag, and in conjunction with the thrust reversers, you can get stopped pretty quickly. A little bit about flight spoilers and speed brakes. I think it's important that you understand that, like it says here, modern jets are so aerodynamically clean that even with power reduction to minimum, it is often difficult to attain the desired descent rates. And it's really a problem when air traffic control wants you to descend at a rapid speed, a rapid rate, but at low airspeeds. Remember, under 10,000 feet, you're supposed to be no faster than 250 knots. So you got to maintain 250 knots and then drop like a rock. So what you really need is to deploy, you know, those ground spoilers that help you, stop the bounce on landing. They can be deployed in flight. And the great thing about the flight spoilers is when you deploy them, you don't have to change the attitude of the aircraft. So you can be going along, and if you're sitting in the window seat, you can see the flight spoilers flip up, and the aircraft doesn't pitch or do anything. But if you were in the cockpit, you'd see some pretty impressive rates of descent, like 4,000 or 5,000 feet a minute. So when you put those spoilers up, you can really drop like a rock and maintain slow speed. So that's an important aspect of flight control for the pilot in the aircraft, in the jet aircraft. That's pretty hard to slow down. Let's talk about speed brakes. The only aircraft I've ever seen, the transport category aircraft that I've seen with speed brakes, was the Fokker F-28. So you may want to Google that aircraft and have a look at it. It had a speed brake on the tail, kind of fanned out. The pilot could select it in the cockpit on landing or in flight, and it would really slow him down quite a bit. So remember, the speed brake are designed to increase drag rather than spoil lift, and are accordingly often installed on the fuselage or tail cone. I'm just reading from here. In comparison with the flight spoilers, speed brakes slow an airplane rather than increase its sink rate. Page 77, and just look at some of these features again. Again, we have an aircraft in a turn. We have the down aileron, so it's turning to the left, and we have outboard aileron, inboard aileron, and then we have roll spoilers at this situation. Now, when it's going to the left, these do not deploy. So on this side, we want this wing to drop down, so we have the up aileron of the outboard aileron, and we have the high-speed inboard aileron up also, and we have the roll spoiler assisting them by automatically raising in harmony with the ailerons. And as we can see here, let's just remember that we have the slats on the outside leading edge of the wing here, and we have the leading edge flaps, the Kruger flaps or the droop flaps usually on the inboard portion of each wing, as we can see here. So just get familiar with those. And what would these spoilers be here? These would probably be your ground spoilers, or you could use them for in-flight spoilers also, as we talked about, to drop out of the sky like a rock without changing the attitude of the aircraft. Let's go down and just talk about the flight spoilers. Down on this one, it looks like it's an old Dash 8 aircraft. De Havilland turboprop, very common in the regional airline business. And so what we see here is the flight spoilers may be used in flight to increase descent rates. On most aircraft, they also deploy automatically after touchdown. So flight spoilers can be used in the air or on the ground, whichever you need to. And again, these are ground spoilers. I'm not sure that these could be deployed in flight, but if they did, it would just increase the descent rate. So maybe they only have the outboard flight spoilers deployed, and those are deployed on the ground for, once you get down and land. And then, of course, they've got the roll spoiler on either side here, which out here and out here, which are used in conjunction with the ailerons. Remember, they're used in conjunction with the up aileron. So they kill the lift and assist the ailerons in making the turn. Section on spoilers. Let's just review this. Spoilers are usually hydraulically powered and may have dual mode of functions for any one panel. For example, roll spoilers may deploy on both sides upon landing in order to function as ground spoilers. Or in flight, they may be used in coordination with the up aileron to assist in the turn. Let's continue on page 78, left-hand column, under Control Tabs and Power Assisted Controls. He talks about in medium to large aircraft, they often require power assisted controls so the pilots can handle them. It is usually accomplished through hydraulic boost and is carefully designed to give the pilot normal field control. So this is a normal situation. The large surfaces need, pilot just can't do it through hand strength, and so they have to have usually hydraulically actuated control surfaces with either a rotational or usually it's a cylinder with a hydraulic rod that will push the control surfaces to where it needs to be. Now, when these power assisted control systems have problems, and usually they're highly redundant. In other words, they have 2 or 3 backup systems, because this is crucial for an aircraft to be able to control the flight surfaces. And so they have a lot of redundancy, but sometimes, as a last resort, they refer to what they call a manual reversion. Reversion means going back to something simpler, and we'll talk about reversion at some point later on. But it means that the operating controls of the aircraft can be manipulated by human strength as a last resort. But that would be extremely difficult. And so, again, it's the last form of defense if you're losing all your other power-assisted things. Let's go down and talk about control tabs. Interesting concept. I first was introduced to the control tab on a Twin Otter aircraft. On the rudder, the vertical rudder of the aircraft, it had a control tab. And so the control tab is like a trim tab that is actually operated from the pilot's yoke, and it uses the trim tab to fly the control surface, in the case of the Twin Otter, the rudder, to the position you wanted it. So you didn't have control cables going to the rudder, you had control cables going to the little control tab. So let's read what he says here. On these airplanes, ailerons and elevators are not directly controlled by the pilots. Rather, the pilot control yokes are mechanically connected to the control tab located on each aileron or elevator. Each yoke input moves the control tab, which in turn flies each control surface to its desired position. So if you want the control tab to go up, if you want the aileron to go up, you'd put the control tab down, and that would aerodynamically push the aileron to the up position, and vice versa. Same with the control tab on the rudder. If you want the rudder to go to the left, the trim tab went to the right and used the aerodynamic pressure on the tab, control tab, to push it to the left. So you may see that, like I said, on the older Douglas aircraft. They use that quite a bit. You don't see it too much on the Boeings or the Airbus. Okay, flight control system redundancy. Now, redundancy means what? Repetition or backing up. So as we'll notice, and here's a good test question, the Code of Federal Regulations, Part 25, or FAR 25, talks about airworthiness standards for transport category airplanes. And here's a little pop-up note here. FAR 23 deals with small aircraft certification, and FAR 25 deals with large transport aircraft, which we're talking about most of the time in this class. And under that FAR, it requires that they do have redundancy or separation of primary flight controls in order to overcome systems jamming. Okay, so he's talking about the redundancy so that if they jam, they can still overcome that. In some airplanes, for example, roll spoilers, which are usually hydraulic, are directly connected to one pilot's flight controls, while ailerons, usually mechanical, with possible hydraulic assist, are attached to the yoke control of the other. As long as both yokes are connected to one another, all controls act in harmony. But in the event of a jammed or inoperable system, a clutch connecting the two systems is released to overcome, allowing one pilot to fly via the operating system. Then he talks about in-pitch redundancy may also be accomplished by splitting the elevator controls, or it may be achieved through the use of alternate power sources for the elevators. If you'll notice that on the 777, the Boeing 777, it has a split rudder. You say, what's that all about? Well, it's that jamming provision, anti-jamming redundancy provision that they have. So each pilot controls one of the portions of the vertical rudder, and so if it's jammed for some reason, the other pilot can still have some control over the aircraft. Down at the bottom of page 78, it talks about the Flight Control Surface Position Indicating System. If you ever sat up in the cockpit of one of these larger aircraft, you often find it's impossible for you to see the wings or the control surface from the cockpit. So to deal with this problem, a lot of large turbine aircraft are equipped with a Flight Control Surface Position Indicating System. And we'll see on the next page over that it's on figure 5-5. We can actually see the flight control position indicator that you'd normally see in that situation. At the bottom of page 79 on the left-hand column, you'll see figure 5-5, which has the diagram of the flight control surface position indicator. So that'll give you an idea of how that works. Before we end this learning module, we'll talk a little bit about the fly-by-wire control system. We primarily see this in the Airbus aircraft coming out of Europe. Does everybody know where they're manufactured? Toulouse, France. Okay, so let's talk about fly-by-wire. Until relatively recently, primary flight control surfaces in civilian aircraft were always mechanically linked to the pilot's yoke. Now they were power assisted, of course, but they were always mechanically linked. Now the military have been using this fly-by-wire system for quite a few years. I know the F-18 way back in 30 years ago, that when they were developing the F-18, it was a fly-by-wire aircraft. So the military has been using these quite regularly for a number of years. So it's not a experimental type system, and that's why the Europeans use it on their airliners. But Boeing's been a little bit slow to come to the party. Anyway, let's talk about on fly-by-wire aircraft, all control inputs are converted into electrical impulses via transducers in the yoke or joystick. Now, as you notice with the Airbus 320s and such, they've got a control joystick rather than a yoke in front of the pilots. So it's an interesting way of controlling it. Some people love them, some people hate them. These impulses direct hydraulic or electrically powered control surfaces through a computer. And these computers, these flight computers, they're backed up. They have backups on the backups. If the computer fails, they really have a serious problem. So they've got quadruple redundancy on these things. There is no mechanical linkage between the yoke and the control surface, only the electrical wiring that conveys the signal, hence the name fly-by-wire, as you can see over here. Precision motors drive control surfaces by computer command. You can see the computer up in front. Transducers convert pilot control inputs into electrical impulses. It goes to the computer to verify, compare, and refine the control inputs to the control surface movements, and then it's directed back to where the control needs to be inputted. Here are the wires that carry it back there. And as you can see, or you can imagine, there's a tremendous saving in weight using the fly-by-wire system. So that's one of the main things. Also, from a mechanical maintenance point of view, if you want to call it mechanical, electric maintenance point of view, you do a lot of swapping of boxes, control boxes, and not very much wrench tightening and loosening and that type of stuff. And so the maintenance on these aircraft is reduced substantially, and they feel reliability of the aircraft is improved dramatically by having the electrical system with the computer interface. So this basically wraps up the learning module on flight controls. Will be pressurization. You'll find that interesting. And so we'll talk with you later. Over and out. Bye.